Yeah, yeah, yeah. Den funkar.
Yeah.
Okay, so we are ready for our first talk. Professor Anders Szepessy is a Swiss mathematician. It's a real pleasure to have you with us, Anders. You received your PhD from Chalmers in 1989, um, and you worked back then on convergence of streamline diffusion finite element method for conservation laws. And Klaas Johnson guided you in that adventure. Um, you are a professor of mathematics and numerical analysis at the KTH Royal Institute of Technology, and your research area is really wide. It's applied mathematics. You you have in your page, at least in Wikipedia, that you say especially partial differential equations, but actually that is just a very tiny part of what you actually do, as you will see, you will show us today. Um, you have been I mean, you have got many accolades, but I will mention just two. You have been an invited speaker at the International Congress of Mathematicians in 2006 in Madrid, and you also are a member of the Royal Swedish Academy of Sciences since 2007, and that is the one that chooses the Nobel Prize, as far as I know. So that's a big distinction. So Anders, the floor is yours. Thank you.
Thank you. Thank you for the invitation. And here is the title of my talk. It is about generalization errors for deep and shallow neural networks, and joint work with Akko Kammonen, Jonas Kiesling, Matthias Sandberg, Peter Pleschak, and Raul Tempone. So I will present theoretical and numerical results on two questions. And the first question is if the Metropolis method can be used to optimally sample in neural networks. And the other question is on the generalization error for deep neural networks compared to shallow. So these are the two questions I will address. And here we see numerical results on, to the left, there are two methods tested. One is standard stochastic gradient descent. That's the small green dots here. And on the axis here, we have the generalization error. And on this axis, we have the number of neural network nodes, so the number of degrees of freedom. And we have chosen a function which is hard to train, and after some while one get the problem with stochastic gradient descent. Although if one continue iterating for a long time, it will eventually work also. And then we have the blue dots here with arrow bars, which is this adaptive Metropolis method that I will try to describe soon. And on the right figure, we compare a shallow network, which is the blue dots here, with a deep network, a deep residual network. And you see it is the same rate, 1/k, but the constant is smaller for the deeper network. So the theoretical basis of neural networks is the error estimate by Baron from 1993, where the generalization error, namely what is on the axis here, is if you want to train a function f with a Fourier transform f hat, then you can bound the error by the L1 norm squared divided by the number of nodes when you have one for a single layer. That is this rate here. And then if we take several layers, you will have this possibility to have L times K here. So we want to know if can we get a smaller error than this for a deep network, and for which functions can it be smaller? Okay, so here comes the plan. I will give a background with introducing neural networks and random Fourier features, and I will give an elementary proof of Baron's result. And then some background on how to sample optimally, what one would like to achieve, and then this adaptive Metropolis method that I mentioned, that in some sense does that. And then the other question about a deep, so I will describe a deep residual network based on random Fourier features and show a theorem, and then try to explain why it works. Okay, so here we have the setting. We are given data xn, so x could be, the data points x could be in RD, and we think that the data points y, they are real valued. And we have a set of them from 1 to capital N. And then the objective is to find, to solve this least squares problem. So I've written it with this Fourier basis here in the beginning, so that where it is easy to prove things. So then we have a neural network. We minimize over both the amplitudes here and over the frequency parameters omega. And the difference in the random Fourier feature setting is that then the frequency parameters are independent, sampled from a density P, and you solve the minimization with respect to the amplitudes like that. And one may then ask, how should one choose the density to sample the frequency? So these are the two settings: random Fourier feature and standard neural network. Okay, so my plan is to give this slide on on writing. So I stop sharing and share and take the other. Okay, so I will do this elementary proof by hand here on the screen. I hope it works. You see everything. So we have a Monte Carlo approximation of a function like this. So we have the function f we want to approximate. We write it in the Fourier representation. Like this. That's the first step. And then we do a Monte Carlo approximation here. Of this integral. So we have capital K samples of the frequency omega, and they are sampled from a density P, which we have chosen, and we call this a function beta of x. This would be a neural network, but of course in practice we don't know the Fourier transform. But now we want to get obtain an error estimate. So the omega k, they are independent samples from the density P, and we see that the expected value with respect to the frequency parameters of the neural network beta, that is the function we want to represent, and the error, which is the variance, is the variance here. I will show you that it is bounded by this quantity here. So that's the variance. These are, I said in the beginning of the talk that it will be elementary, and here is this elementary part, I hope. So how do we prove this? So let us write down the variance like this. Then we know that here we have the representation of beta. So if I write down this, use that expression, the variance is written as a double sum like this. So we have one sum over small k and one sum over L, and then we have the first factor, and then we have times another similar factor with complex conjugate. Okay, so by the property here that the mean of the neural network is the function f of x, the double sum that we have here will become a single sum, and we have k of these terms. So then we only obtain the square of the like that, and that we can simplify to the expression we have here. Okay, so that is the basis of Baron's proof, and in the simple setting where one have a representation of the function with the Fourier transform like that. Let me go back to the other screen now. Okay, so how do we obtain? We want to measure the error in the mean square sense like this. And the neural network tries to find the minimum using all parameters. The minimum will be less or equal to the mean here, taking the mean instead of the minimum. And this expected value was what we just computed in case of the Fourier representation, which decayed like 1 over k, as we saw here. And Barron's proof is for a general representation like that. Then the idea is the same, but the difficulty is to show that one have a representation of this kind for any function under some conditions. Okay, so now I said we want to understand what is a good density to sample from. That is important for the random feature setting. So then we can think like this. I would like to minimize this expression with respect to probability density. So what I want to minimize is the Fourier transform squared divided by the density. That is what this is the error constant that we saw in some way in the first figure here. The slope here is related to that constant, and we will see. Now we want to estimate how large or how small can this be. Then we represent p. This is a probability density, so it has the constraint that the integral should be 1. So if we write p as a general function q divided by the integral of q, then we can vary q freely, and if we take the first variation with respect to q, then we obtain this variational form. We differentiate with respect to q, then we have 1 over q squared here times the test function, and then when we have the test function, we differentiate with q here, and we obtain, for this to be a solution, we obtain that the Fourier transform absolute value squared divided by q squared should be constant. And if we plug in the definition of p, that is q divided by the integral over q, we see that the density, the optimal density, will be proportional to the L1 norm to the amplitude of the Fourier transform divided by the L1 norm. And now I have a question. So in the neural network, of course we don't have the Fourier transform. We only have this is what we have. We have the basis functions with some frequencies, and we have the amplitudes. And we would like to sample omega from the optimal density, which is proportional to the Fourier transform of f. So how should that be possible? And we don't have the f, and we would like to sample from this density. But we have the amplitude. So here comes the algorithm that produced the first figure I showed. So given that we have the frequency set omega 1 to omega k with the corresponding amplitudes beta 1 to beta k, we make a random walk proposal of a new frequency omega prime. So we have k of these omega primes, and each of them is in RD. And then for this proposal, we solve the least squares problem to determine the amplitudes. So we have beta prime, which for the frequencies omega prime tries to, in the least square sense, approximate the data. And now comes the Metropolis test, which is that we accept the new proposed frequencies with the probability related to the quotient of the amplitude's absolute value to the power of gamma. So if the quotient of the amplitude in this way, this is our acceptance test. And the motivation is as follows. So when we did the derivation up here, the derivation. So if we would have the Fourier representation, then the amplitudes here will be Fourier transform divided by k times p. So if one believed that in the asymptotic limit one would have that, then so the amplitudes have this representation, but by the Metropolis test, the density will then be this quotient to the power of gamma. So if we solve for the density, we see that the density will be proportional to the Fourier transform to the gamma divided by gamma plus 1. So if gamma is large, we will almost sample from the optimal, which is the Fourier transform absolute value. And it is costly to have very large, because then we get large numbers. So that in a balance the work, we choose it to be 3D minus 2 here. That is we fix that parameter. So then we have an algorithm here that produces the result in the first figure here. And I will show you later which test functions we have used here. But it is a function where the Fourier transform in L1 norm is large. If it is small, it is easy, and all methods will work. Okay. So let us see what happens if one take other activation functions. So the algorithm, the same algorithm using other activation functions. So instead of the Fourier representation cosine, or then we tested here with the sigmoid activation function the arctang and the ReLU, and they behave similarly, that the generalization error, the case like 1 over k, as you see here in this figure. Okay, so here, now we come to the second part of the talk. Why can one explain in some way how that the deep network gives a smaller realization error than a shallow network, using the kind of ideas that I presented for the adaptive Metropolis? So here is the setting. We are again given data where each x endpoint is in RD, and yn is a real valued number, and then now we have a deep residual network. So the residual network is given by this constraint here. If we put capital L equal to 1, then we have 0 here, and then we don't need, we could take only this function here, and we'll obtain a standard shallow network. If we take L larger, one in each layer have the standard network, but also another network which depends on the state variable Z here. And in the end, one wants the state variable to be close to the data point, with a penalty depending on the difference, namely these network functions. So we view this as a random Fourier feature setting, as we did for a shallow network, but now we have frequencies for the x-dependent basis functions. They are sampled from a density p prime, and then we have this state-dependent basis, which is sampled omega from another density p. So it's important that we have this standard network in each layer. So here is our theorem. We assume now that we have data points that approximate a function f with some noise epsilon, which has 0 mean. And the first step is that to find we assume that we have a function h, which is real valued from R to R, which is a Schwartz function that equals 1 on the interval -1 to 1. And then we assume that the L infinity norm of the function f is bounded by f, and we assume that the Fourier transform divided by the density, this was what appeared in the estimate for the constant in Baron's estimate of the generalization error. So we assume that this is bounded, A, and then some other quantities related to the Schwartz function f, h here, some other quantities related to that function. So a Schwartz function is a function which is differentiable to any order, and the case quickly when you let at infinity. So it decays quicker than a polynomial at infinity, and it is differentiable to any order. So Fourier transforms are well defined, and then we assume that that it has a bound of this little bit complicated type. And then we look on on this neural network here, and we assume that we have found the optimal solution to this optimization problem that we have here. That we have data points here and a neural network generated by this residual neural setting. Then, in fact, this optimal residual neural network has the estimate that the case like a constant divided by the total number of nodes. So we have L layers, and in each layer K nodes. And then we have smaller arrow terms that are here, depending on the noise and the penalty parameter. And the important thing here is that the constant in the dominating term here, which is C, that is basically B star squared. And it depends also on A star. A star is the optimal value we could achieve. Namely, in the Baron estimate, we had Fourier transform square divided by P prime. But if we take the optimal density, we have F squared divided by F here. So the optimal is constant is the L1 norm here, L1 norm squared. That was on the first slide. You saw it here, L1 norm squared. That is the optimal estimate. Okay, so the question is, can this constant be smaller than A star squared, this constant C? And that, in fact, it can if one choose the densities P and P prime to depend on the layer. So in the first layers, so the layer, I denote them by T here, which is in the continuous setting, it corresponds to the layer L divided by the total number of layers. So asymptotically, you first only use the basis functions related to the x-dependent the basis functions, and that you use up to a certain layer, namely B star divided by A star. And then after that, you use only the basis functions. So in the beginning, you use only these basis functions. And then after a certain layer, you use only these basis functions. And of course, one need to find the constants C and B. So in the case that the L infinity norm of the function f you look for is small compared to the Fourier transform in L1, then actually the constant C here, that appears here, is smaller than A star squared, which is the shallow network bound. And that is this figure showing. So the shallow network, that is the blue, that is L equal to 1 shallow. Then you get this rate sort of 1 over K, but with a bigger constant than these 5 layers green dots here. Okay, so now let me try to explain how this could be. Okay, so we want to see how could this result, what is the thinking behind this result. So the first idea is to look on an continuous setting that that approximate the discrete. So then in the continuous setting, we take infinitely many layers. And we have an optimal control problem with a differential equation constraint, where we have basis functions here and an integral, Fourier integral, and another integral here, which resembles the two networks we have here, with if you take infinitely many layers. Okay, so we want to understand this optimal control problem and solve it by hand. Okay, so here the control functions alpha, the control functions, they depend on the data point x, which means that we can when we look for this mean field optimal control problem, we can optimize with respect to each data point x. So for each data point x, we want to minimize what we have here inside, which is what we have here, with the differential equation constraint like that. And this optimal control problem can be easily solved directly. And the solution is to go from, so we start at 0, so is to go from 0 to the data point y in a straight line with a line with respect to t here. So the state variable at time 0 is the state variable 0, and at time 1, which is the final layer, you are at basically at y, but you have the penalty coming from here, so little bit perturbed y. So that is the optimal solution for the state, and it has two representations. So you can represent the control like that or like that, which we do in the next step here. So that the control alpha, when we write in the discrete setting, then we think of the part coming from the basis function depending on the state. They approximate the scale identity map, and the standard Fourier feature basis functions, they approximate the data. So in the beginning, gamma here is close to 0, and you only have this and not that function. And after, in the final layers, this becomes small, and instead that scale identity map is used. And so this is a kind of bang control for the control gamma, and it has this splitting of using the standard functions with the y map and the residual state variable with this cutoff identity map. So here are the ideas in the proof. There are 5 steps. The first is to relate the minimum approximation of the residual neural network to this infinite optimal control problem that I described. So relate that, and then we want to have an error representation of this discrete compared to the continuous, based on an approximate value function along the exact path. And we need to estimate these value functions, derivatives of that. And we want to also to estimate the error between the approximation and the infinite, and use the Monte Carlo. The Monte Carlo is basically what I wrote here. So here comes some numerical tests. Now I take a function which is this function. So the underlying data is to approximate this function in x1 direction, and in all other directions it is Gaussian, like this. So we are in dimension 4 here now. So this function has almost a discontinuity here, and the slope is related to 1 over a, and this oscillates by construction, this function, a little bit here. And here are numerical results testing the deep residual network that we constructed. So the blue line is the 1 over the total number of degrees of freedom, L times K. And then you see the small red dots, that is a shallow network with 1 layer. They go like that, like 1 over K with this constant. And then we have compared with a dense, fully connected network with real low activation function. These are, you see them here and here. And then we have this residual network, which is given for different number of nodes in each layer. Here we have 8, and then here we have 64, and then these are 512 in each layer there. So for this function, the L1 norm of the Fourier transform grows like the logarithm of 1 over a. Yes, I am. Yeah, okay, so let's see. I thought first that the talk was 45 minutes. So are there any questions?
Yeah, Anders, I'm here. So any questions at this moment from the audience? Okay, I can give you a question. So in all these approximation properties, and there's a hidden some kind of intuition, right? That when you go high dimensional, you expect to have some kind of concentration of information in some low dimensional manifold, right?
Yes.
So, in the estimates that you have, essentially, this is not so apparent, right? One has only a control on the norm in a certain space, and that would be enough to get this approximation. In the numerical example that we have there, we have dependencies only on x1 and on the radius, right? So there's a hidden, say, manifold that only contains 2 dimensions, so to say, x1 and the radius.
Yes.
But the norm plays an important role. So
yes, that's right. So if one would take, also if I share again.
And by the way, 45 minutes is fine. I mean, it's not that you're obliged to go to the whole thing, because discussions.
No, maybe I could go to details to the proof, but that I don't want to.
No.
Let me show you. It's better with questions if you have any. So that if you take a general function f and compute the Fourier transform in high dimension, that that will typically be large unless you have low dimensional features. So this number will be large if you just take any function in high dimension. So, I mean, it is difficult to approximate a function in high dimension if you don't have some special properties of the function. Namely that the Fourier transform in L1 is not too big.
Yeah.
And
but I mean,
so this is a measure of low dimensionality.
Excellent. Yeah. Any more questions? Comments? Complaints?
Yeah, complaints are fine.
Yeah. No, I think if there are none, we can thank this. Well, there's one. I mean, Joachim has one. So Joachim, you can use the mic.
Hi, Anders.
Hello.
Could you talk more about the difference between this shallow and the more kind of deep? And what are the insights that you have gained by doing this work?
Yeah, that's a difficult question, but the insight. So the insight. Let me try to review a little bit what. Okay, so now let me write down the. Okay, so we have here is the deep residual network, which is a mean field problem that you have a constraint here, which is like discretization of differential equation, and the reason we could, I mean, go somewhere from is that we included this standard neural network in every residual step here. That makes the control depending on x, and that when the control is depending on x, then this so one have a control depend in the continuous setting with. So our intuition was to think about the continuous setting with infinitely many layers. Can we understand how the residual behaves? Okay, but if we include these basis functions in the residual neural network, then the critical step was this step that you can solve this directly for each x. You have the solution for each x, namely a straight line going from 0 to y of x, basically. That is the state, what the state is doing, which is very simple in a way. So could one, that was the intuition. Since that we have that simple description of the optimal state variable, then comes this idea that okay, the identity map could be simpler to approximate than the whole function y, and that is the intuition about how we think in this setting.
Thank you.
I don't know if it answers your question, but
I was thinking about approximation quality in terms of that. It seems like you get some kind of variance reduction. Is this the thing that when you went from
it is still with this setting that one want to find the optimal frequencies here and here in this random Fourier feature setting, and that is always a challenge to find that. So the first part of my talk was to, if one have just one single layer, how can one try to find these densities? So I think that is a basic question, which is maybe more important than a deep network. That if one have a systematic way to sample from the optimal, then one will obtain this estimate always, and not this kind of setting that stochastic gradient descent presents. But it is difficult, because if we do stochastic gradient descent with high function that has high frequencies, it very slowly find the high frequencies. If one don't know them a priori, which one don't. So then the stochastic gradient descent will find high frequencies, but this process is very slow. And then when one do Metropolis, it's also difficult, but in some way one need then compare the computational niches, comparing this and that method.
Thank you.
Yeah.
Thank you, Anders. That is the spectral bias, right? What you were talking about.
Yes.
Yeah.
So there is a paper by Jonas Kiesling on spectral bias where we want to precisely define this spectral bias.
Yeah, very nice. Okay, so if there are no more questions, we can thank the speaker once again. Thank you, Anders.
Thank you.
Yeah.
Yeah.
Very rude. Yeah. Okay, so now we get the next speaker set up. We have 8 minutes still, so you can relax, take a little bit of coffee, and we clap when you have to go back. Okay? Thank you.